Right, the final topic in lesson number 6 again falls under the broader heading of two-sample t-test. Is the second bullet where we compare proportions of two independent populations, and we use the Z model, mean zero, standard deviation 1 for these. But again, it's going to follow the structure of the previous two. The independent and dependent samples t-test will use technology to create and do the messy calculations. So again, from 30,000 feet, the one we're examining, the tests that we're examining in this video are population proportions. So you might think about we have proportion 1 and a proportion 2, and we're going to examine the percentages. So the goal is just as I stated. We have some assumptions that we'll go over in just a second. And the the point estimate is just the difference of the proportions. So let's say that there's a presidential candidate. Let's just call this person candidate A, right? And we want to see if there's a difference in the percentage of people from Kentucky who are going to vote for this candidate versus the percentage of people from Ohio. So I may let pi sub 1 be the percentage of Kentuckians who intend to vote for this candidate, and pi sub 2 is the percentage of Ohioans who intend to vote for this candidate. So my point estimate is just percentage 1 minus percentage 2. Now my point estimate for the difference is P1. That would be the percentage, that would be the sample I take from Kentucky. And then P2 would be the sample that I take from Ohio. So let's say I take 1,000 people from Kentucky and I find out that 580 are going to vote for this candidate. Then my P1 will be 580 out of 1,000. Let's say from Ohio, I pull out 1,000 people and I find that 620 are going to vote for this candidate. Then P2 would be 620 out of 1,000. Now, the assumptions are that n times P and n times 1 minus P for both populations are greater than 5. Now, the pooled estimate for this type of problem, so we call that like the average P, if you will, is just x1 plus x2 over n1 plus n2. You really don't need to know this to be able to carry one of these out with StatCrunch. Just presenting the structure of the test to you. The test statistic is ugly. It is just write down ugly. P1 minus P2 minus mu1 minus, or I'm sorry, pi1 minus pi2. That's usually 0 because we assume that pi1 is equal to pi2. So really the numerator just turns out to be P1 minus P2. The standard error, just take a look. It's just kind of ugly stuff, right? Just is. But again, we do all of this using StatCrunch. The null and alternative hypotheses are a function of whether we're doing a lower tail, upper tail, which again, those are both one-tail test, or a two-tail test. That should look pretty familiar. It follows the model of the independent samples t-test that we studied previously. So that should look familiar as well. So an example, is there a significant difference between the proportion of signups generated by two different web page designs? So it looks like in an experiment that 387 of 4325 signed up for design 1, 283 out of 469, or actually 4,639 signed up from design 2, test at 0.05. Well, hypotheses, pi1 minus pi2 equals 0. That's telling us that the proportions are equal. The alternative hypothesis is we're testing that they are not equal. So the sample proportions, design 1, it looks like about 8.95% signed up. Design 2, it looked like about 6.1%. Now, if we're only concerned about the sample proportions, then we're done. But if we want to uh, use the process to generalize about the two designs, which one is better than the other, or if there's any difference, then we have to use inference procedures, hypothesis testing, and confidence intervals. So the pooled estimate, pretty easy to calculate, just x1 plus x2 over n1 plus n2, 7%, 7.5% about. Critical values for a 0.05 two-tail is 1.96 plus or minus 1.96. Our t test statistic is 5.1228. It falls outside the bounds, so we reject H sub O. So we determine that the percentages are different. Next thing we'll do is calculate a confidence interval. Notice that the confidence interval 0.0175 to 0.0394 does not contain zero, which corresponds to rejecting that the difference is equal to zero. And so we can be, there's a 0.95 probability that the difference in the two proportions is contained in this interval. All right, let's do it. Let's go to the remaining question. Get over here to it. So looks like, I think there's only one question remaining, right? Yeah. So we have n1 equal 100, x1 equal 90, into 100. So that tells me that 90 out of 100 for sample one had whatever we're testing, and 70 out of 100 of sample two. So we want that the proportions are equal because we're testing a significant difference, not pi 1's bigger than pi 2 or pi 2's bigger than pi 1. We're just testing a significant difference. Calculate the test statistic. Well, I'm going to need StatCrunch. So let me get organized here. And I am going to go to prop stats to sample with summary. Should be pretty obvious why I chose that. So for sample one, we have 90 out of 100. Now I'm going to make a mistake here. Someone, I wish you were here. Why can't that be true? And what's going to happen if you try to proceed that way? It's going to give you an error. The reason is the successes has to be less than or equal to the observations. So I've seen students do that before and get all wigged out because they couldn't figure out what the issue was. So our hypothesis, null hypothesis, P1 minus P2, again, same thing, pi 1 minus pi 2, same thing as P1 minus P2. Show our critical value, we're testing at 0.05. So let's compute. So the test statistic is rounded to what, two places, so 3.54. The p-value is to three places is 0.000. So since our p-value is less than our alpha, 0.05, we're going to reject the null. So there is sufficient evidence to support the claim that there's a significant difference between the two population proportions. Calculate the confidence interval. All we have to do is go up here and hit edit, click a different box. So it looks like, what are we rounding to? Four places, so 0.0926. and 0.3074. Hopefully I didn't do a typo. And oh wow, that's it. All right, cool. Take care.